These figures are from this paper by Choi et al., Overcoming the Diffraction Limit Using Multiple Light Scattering in a Highly Disordered Medium. On the upper left, we see a comparison between a conventional imaging system where we're going to use a set of lenses to image an object. And then B and C here show that, first of all, rays that from the center of the object that would normally be lost to the imaging system can be scattered by this turbid media such that they go through the lenses and are captured by the sensor. And similarly, if the object is shifted outside the normal field of view of the lens, those rays can be captured and the object can be imaged potentially with higher resolution. The images at right show experimental data. A is using a high numerical aperture lens to image an object. In B, a lower numerical aperture lens is used, and you see that now certain features are unresolved and certain lines in A are lost. C is experimental data of images taken through a turbid media. So we have a lot of scattering of a coherent field, and the field that we see is highly disordered and speckled. But by computational processing, one can recover the image shown here in D. Today, we're going to talk about how this works. Computational Imaging. Episode 34, Imaging through Inhomogeneity. Episode 33 considered a variety of methods for imaging off of a scattering screen. So we can see around corners, or we can get improved super resolution by imaging the field observed on a two-dimensional scattering screen. Much more commonly, we observe an object through a three-dimensional scatter. Here we have a remote object, and the field propagates from the object through a turbid medium or otherwise scattering material, which could be, for example, the atmosphere, or it could be tissue. There's a wide variety of situations where the field propagates through an inhomogeneous media. Now, if the media is static and one can calibrate the modes coming through the media, propagation can be modeled either forward or backward through the media. So one could back propagate through on the modes that propagate through the media and image independent of the scatter. And as we saw in the introduction, one could even hope to get improved resolution by using the properties of the scattering material. But in some cases, the scatterer is unknown and one seeks to image through the material. So one of the methods that's been developed for that situation is this ballistic photon imaging. In this case, light that propagates most rapidly through the material will be the least scattered, and so one can filter on the light that is propagated at a very short time, basically equal to the speed of light for propagation directly through the material, and obtain unscattered light through the material and image through this inhomogeneity. Here we have a paper by a kind of all-star cast of investigators led by Sina Farsu, where at the top we see an image observed through a scattering material with conventional imaging, and at the bottom we see images obtained by this isolation of ballistic photons coming through the material. Alternatively, one can seek to characterize the scatter and image by backpropagating through the scattering material. Full wave model characterization of what happens in the scattering material can be very difficult, but if one learns sort of the impulse response for different stimuli, then one can hope to invert the scatter without directly knowing the full three-dimensional structure of the scatter, but just characterizing coherent modes that propagate through the scatter. This is done in this paper by Ramani and others, where we have a multimode optical fiber. So we're observing a material propagated through a fiber, and of course the multimode structure of the fiber scrambles the signal coming through. So here we have various digits that are various symbols that are sent through this fiber, and we observe a speckle pattern at the end of the fiber. In this case, this is inverted using a neural network. So one applies a variety of stimuli, measures the output, trains a network to regressively reconstruct the input from these output speckle patterns, and then one can test that with unknown speckle patterns and generalize to image through the fiber. This method has been applied by a variety of groups. Of course, one of the challenges is if the fiber changes, if, for example, the fiber is bent or temperature changes, one may find that the speckle patterns change. So continuing research focuses on ways to characterize, calibrate, and track those kind of changes in image through the material. We don't have time to analyze all possible ways of imaging through scatter. Today, we're going to just introduce a simple mathematical way to analyze this system, to introduce the main concepts of this. This is our last lecture in Chapter 5 of Computational Optical Imaging, with our focus on wave imaging. And in our next lecture after this one, we'll be able to introduce optical elements. But today, let's consider this simple model system. So we have a one-dimensional system where we have a input signal field shown on the left here, and it's going to propagate to a phase screen, be modulated by the phase screen, and propagate to the output. Now in this case, we actually are dealing with a simple one-dimensional phase modulation. We could model a volume phase modulation by putting in multiple phase screens using the same methods that we'll talk about today. But we're assuming that as with a fiber or other sort of intermediate inhomogeneity, that we're measuring this encoded field that's been distorted by the inhomogeneity between the object and the measurement screen. So this system is analyzed in this Python notebook, which is available on the GitHub site corresponding to this system. And the main point today is to look at numerical methods for analyzing propagation through inhomogeneity. Now, in this case, we're going to model this system by assuming that we have a Gaussian beam as our impulse response. So this is the forward model without the inhomogeneity. What we see on the columns here is the output for various inputs, and here we assumed even though the input space is 200 wavelengths across, we're going to model it with 1024 impulse positions. So we've oversampled the impulse position, and for each impulse, we get this the response that you see on the vertical column, which is the sort of output of a Gaussian beam, and this is the real part of the beam. The beam is actually, of course, complex. So this is the H matrix, the forward model for propagating from the input plane to the output plane with a free space version of this. Now, the reason that we're modeling this with this discrete H matrix instead of simply using, for example, the angular spectrum method is that the angular spectrum method requires us to have a space with enough padding that we won't have any aliasing effects. And here we're going to assume that we're going to measure the output field over the same finite 200 wavelength across space. So we want to build into our model the ability to limit the support of the output space in an efficient way, and this discrete H matrix is not computationally efficient as it would be if we did the fast Fourier transform methods, but for this kind of modest scale problem, it's definitely computationally tractable and allows us to not have to deal with padding and aliasing effects. So we have this H matrix, and what will happen, so this is, we have a certain number of inputs and we see the Gaussian beam outputs, and if we increase the range between the input plane and the output plane, then this Gaussian beam will expand in size, and so we'll have a more blurred output from the inputs. And we can analyze the difference as we increase the range between the input plane and the output plane using singular value analysis. So this is the singular value spectrum for a free space propagation from a input plane that's 200 wavelengths across to an output plane that's also 200 wavelengths across. And we're looking here at the singular values. This is a measure of the conditioning of this system, how many modes propagate through. So if the distance between the input plane and the output plane is 200 wavelengths, we get this blue curve. And so here, we have 200 wavelengths, and we're seeing somewhere close to 400 non-zero singular values for different modes that propagate through the system. As we increase the distance between the planes, the field diffracts to a larger and larger area, and less of the rays coming from the object are captured by the input plane, but equivalently we can say fewer modes are captured. So if we go to 1,000 wavelengths, we have less than 100 modes captured by the system. So this is analysis of the singular values. We can similarly analyze the impact of increasing the distance between the planes by inverting the measured field at the output to estimate the input object. So in this case, we're going to assume that the input object is this one-dimensional set of two square waves, very similar to the work by Choi et al. That we saw in the introduction. So we have two square wave signals, and this is the horizontal axis here is in wavelengths, and so each of the square waves is about one wavelength across, and we're estimating the input field from the output field using least squares analysis with a conditioning number. So we're basically doing truncated least squares to do this estimation. And on the upper right, we see that if there's 200 wavelengths across, or 200 wavelength separation between the planes, we have enough information to resolve at this kind of scale. So we see the two inputs with this estimated signal, and then at 500 wavelengths, the signals start to blur into each other. And if we go 1,000 wavelengths, then they've blurred, and we're only seeing one response from these two signals. So this is what we see if there is no inhomogeneous media between the planes. So go back to our problem here. We have the input plane and the output plane, and now we're going to insert a phase screen between. We model the phase screen as a continuous phase modulation with in the model in the notebook. We assume 256 random phase values, and then we've interpolated a continuous phase screen from those random values. And so we build this exactly the same kind of H matrix. So we use the Gaussian beam impulse response to build a forward model for propagation from the input plane to the phase screen. We then multiply each pixel in the propagated field by its corresponding phase modulation of the phase screen, and then propagate from this phase screen to the output using, again, the same kind of H matrix. Now, if we take that forward model, which is going to have a speckled field at the output, we see this singular value analysis. So the red curve here is for 1,000 wavelength separation between the input plane and the output plane. So the same curve we've had earlier with no phase screen. And then the subsequent curves, the yellow, blue, and green curves, correspond to the singular value spectrum when the phase screen is placed at various ranges between the input and the output. So if the phase screen is close to the input plane, and if we put the phase screen exactly at the input plane, that doesn't really change the modal structure of the signal that we would get through. We've already assumed that the input could be random, so multiplying the signal by a random phase screen doesn't change the sort of modal density that comes through. But as we move the phase screen away from the input plane, then rays that would propagate off at steep angles, as we saw in the introduction, are now scattered into the collection aperture by the phase screen, and we start to see an increase in resolution. But if we moved the phase screen, too far over, close to the output plane, then the rays would have missed the phase screen and wouldn't have had time to refract into the input or diffract into the input aperture. So again, the resolution is not increased, and so we find in this particular case, for this, the phase screen also happens to be 200 wavelengths across, that the maximum increase occurs when the phase screen is exactly at the midpoint between the two planes. Now, the increase in number of modes is not enormous, so we've gone from, let's say, 80 modes with no phase screen to around 150 modes possibly with the phase screen, but the impact on imaging is dramatic. So here is the plots that we see when we use the same least squares analysis in blue. with the phase screen at the midpoint to resolve those two input pots and two input signals, and we see that we have resolved the two signals with the phase screen, and then the yellow curve is what we had without the phase screen. So we have definitely increased the resolution of the system. Now here the phase screen is random but known, so we would have had to use a holographic technique or other strategies to characterize the phase screen with a known stimulus. But after we've done that, then we can backpropagate the field through the phase screen and recover the image that you see here. Now you might wonder, how can we do so much better with the phase screen than without the phase screen when the increase in the number of modes transmitted through the system was not dramatic? And here you might recall from our analysis of singular value analysis of imaging that the conditioning is important. The number of modes that propagate through the system is important in analyzing the systems, but the structure of the singular vectors is also important. Here we compare on the left the first 50 singular vectors for imaging through this system without a phase screen, which corresponds basically to the harmonic frequencies that you get in the plane wave impulse response for propagating through this system. And on the right, we see the first 50 singular vectors in object space with the phase screen. And so the horizontal axis is the object space. Here we're going from -100 to 100 wavelengths. So these are the features that we're imaging with when we analyze these components of the forward model. So the fact that the singular vectors on the right have such high frequencies and such dramatic structure is what allows us to improve the resolution of the system. Even though the total number of modes maybe is increased by a factor of 2, the overall singular value spectrum is actually decreased somewhat. It's not as square as it was with free space propagation, but we have this much higher frequency response, and that allows us to achieve results like we saw with Choi et al. That by characterizing, and in the case of Choi, they measured 2,000 different impulse signals, characterized the transmission through the turbid media. So basically experimentally collected the data that we collected in simulation with the notebook that I just showed you, and they were able to achieve this result of a super resolved imaging through a turbid media. So very, very interesting. And now through the last sequence of episodes, we should be fairly expert in understanding how to mathematically propagate fields through free space and through scattering media. So we learned how to propagate. We learned how to measure the field with holography and with phase retrieval. Then we learned how to image objects using diffraction tomography and compressive diffraction tomography, which consists of applying constraints to the reconstruction that allows us to reconstruct from incomplete data. We discussed temporal imaging, which is helpful with ballistic photon imaging and other strategies. Now we've talked about imaging around and through scatter, but obviously this introduction of a turbid media is not actually the ideal way to image. For that, we should introduce not random media, but optics. And so next time, we are going to start to discuss how to build imaging systems where we'll still continue to use computation, digital computation to form our images, but we're going to use lenses to help make better data. So let's get into that in episode 35.